Prim's algorithm versus Kruskal's algorithm. Both Prim's algorithm as well as Kruskal's algorithm are greedy algorithms for finding minimum spanning tree of weighted, connected and undirected graphs. Then the question is, what are the differences between Prim's algorithm and Kruskal's algorithm? Both the algorithms solve the same problem, but they apply different techniques, different methods in order to solve the same problem. So let us see what are the differences between these two algorithms. Let us start from the first step itself. What happens in case of Prim's algorithm? It always starts with a single starting vertex and then it will expand on it to form the final minimum spanning tree. What about Kruskal's algorithm? In case of Kruskal's algorithm, it starts with a single edge and then it will expand on it and finally form the minimum spanning tree. And what happens at each step? In each step, in case of Prim's algorithm, you will add whichever is the minimum weighted edge that is connecting a vertex which is already in your MST to a vertex which is not yet part of your MST. What about Kruskal's algorithm? In Kruskal's algorithm, you will add the smallest weighted edge that does not form a cycle with whichever edges you are already having in MST. So in both cases, you are searching for minimum weighted edge, but the difference is in condition. In case of Kruskal's algorithm, you simply find whichever is the minimum weighted edge and then you will make sure that it will not form a cycle. What about Prim's? In Prim's, you have to find that particular minimum weighted edge which is crossing the set of vertices which are already inside MST to the set of vertices which are not yet in the MST. This is the difference. Then, what about the MST structure that you are forming? The MST structure at every single step of the algorithm, in case of Prim's algorithm, the MST structure is always connected. And what about Kruskal's? In Kruskal's, you can say that. Why is this so? Because in Prim's, what are you doing? You have one set of vertices which are in MST and then you will add a new vertex to this MST set. And when you are adding a vertex, you are also adding the edge which is connected to that vertex, which means whichever vertices you have on the MST set, they are all connected together. So always your MST that is getting built in the Prim's algorithm will stay connected. But what about Kruskal's? Though you are always looking for the minimum weighted edge, it is not necessary that it should be connected. So maybe your minimum weighted edge in the graph is this. The second minimum weighted edge may be somewhere here. Then the third minimum weighted edge may be somewhere here. So it is not necessary that they stay connected. Sometimes it may be connected in Kruskal's, sometimes it may not be connected. But at the end of algorithm, in both cases, it will all get connected together. This is the difference. Then, what about the data structures used? In case of Prim's algorithm, you can use min heap data structure. Why are you using this? In order to detect whichever is the minimum weighted edge that is crossing the cut. And in case of Kruskal's algorithm, we used disjoint set data structure. It is also called union find data structure. What about the input? The input, depending on the input that is provided, Prim's algorithm changes. That is, if you provide input as an adjacency list, in this case, Prim's algorithm can be done using min heap and that can be done in order of E log V time. And what if it is an adjacency matrix representation? If it is adjacency matrix representation, you need not use a min heap. Instead, you can do a linear search on the array and you can do in order of V square time. This is in case of Prim's algorithm. What about Kruskal's algorithm? In Kruskal's algorithm, whatever be your case, you will always want to sort the edges. So sorting the edges will always take order of E log E time. You can also call this as E log V. We had already discussed why it is in the lecture on Kruskal's algorithm. And then in order to do the union and find operations, you will take order of E into alpha V time. What is alpha? Alpha is inverse Ackermann function. So this is what we learned about Kruskal's algorithm. So totally you can say it takes order of E log E in this case, or maybe E log V, whatever you want to call. This is the case with Kruskal's algorithm, but in Prim's, depending on the input representation, you have two options. One is E log V and the other is V square. Next question is, when should you use these algorithms? What is that case where this particular algorithm works the best? So the answer is, Prim's algorithm works the best whenever you have a dense graph. Let us say your graph is so dense, something like this. It is having lot of edges. So you have some vertices and a lot of edges, such that the number of edges is order of V square. If this happens, that means your graph is a dense graph. In that case, Prim's algorithm works faster, because if you give adjacency matrix representation, you can complete algorithm in order of V square time. You have order of V square edges in the graph. Still, your complete Prim's algorithm can be done in order of V square time. Because of that, whenever you have a dense graph, Prim's algorithm is the best to go for. And whenever you have a sparse graph, your Kruskal's algorithm is better. Why is it better? Because here you have E log V as time complexity. So in case of a sparse graph, what happens is number of edges will be order of V. This is when you call it as a sparse graph. If it is a sparse graph, then Kruskal's algorithm time complexity will be order of E log V, which can be written as V log V. So V log V is better than order of V square. Because of this, you can go for Kruskal's algorithm whenever you have a sparse graph. And one more thing, when you have a sparse graph, if you use adjacency list representation and you go for Prim's algorithm, that can also be done in order of V log V. So E log V will become V log V, because E will be order of V in case of sparse graph. E is the number of edges, V is the number of vertices. Then the other comparison can be based on the space complexity. Let us say if you are looking into space complexity, in case of Prim's algorithm, here both of these will be taking order of V plus E in case of space complexity. So you can't say one is better than the other. And one more thing is cycle detection. You know that MST will not have a cycle. Whenever you want to form a minimum spanning tree, or if you want to form any spanning tree, it will surely not have a cycle. So there cannot be any cycle in the MST. But in case of Prim's algorithm, cycle detection is implicit. What did I mean by implicit? Implicit means I don't have to specifically see and make sure that cycle won't be present. Automatically, when the algorithm runs, it will make sure that cycle will never be formed. How is it made sure? Because you are always forming an edge which is crossing from the MST set to the set of edges that is not in MST. That means if you take any cut, there will only be one edge in the Prim's algorithm that crosses that cut. If you want to form a cycle, there should be two edges crossing any cut. Here, this cut is crossed by at max one edge in case of Prim's algorithm. Because of that, cycle detection is implicit. Automatically, whenever you apply Prim's algorithm, there will be no cycle at any point of time. And what about Kruskal's algorithm? Here, it is explicit. It is explicit. What did I mean by explicit? It is because here you have to specifically make sure that there is no cycle. You will use union find data structure, also called as disjoint set data structure. The whole purpose of using this disjoint set data structure is to make sure that whenever you add an edge, this edge won't form any cycle. So you want to form an edge between disconnected components. Because of this, you are using disjoint set data structure in Kruskal's algorithm, and explicitly whenever you are selecting an edge, you have to specifically make sure that cycle is not present. So you can say cycle detection is implicit in Prim's algorithm while it is explicit in case of Kruskal's algorithm. These are the major differences between Prim's and Kruskal's algorithm. Keep in mind that we use both these algorithms for solving the same problem. It is exactly same problem. Both are greedy algorithms. All those are similarities, but they use different techniques, and because of that, it has these differences between these two algorithms.